In this video, we are going to provide an overview of our work titled GraphMimic Graph-to-Graph Generative Modeling from Videos for Policy Learning. Imitation learning from demonstrations has become an effective paradigm for teaching robots to perform diverse behaviors. However, demonstration collection often necessitates substantial human effort, posing a bottleneck for robot learning. Confronted with this challenge, videos emerge as a promising alternative, offering a rich data source encompassing behavior and physical knowledge. Recent research attempts to leverage video data by pre-training models to predict subsequent images or points from the current ones. Then, leveraging such predictions to guide policy learning on action-labeled data. While these approaches have demonstrated potential, they directly model representations from pixel space, neglecting the modeling of important structures. Correspondingly, graph representations inherently encode spatial relationships, enabling effective structural modeling. Furthermore, we can directly incorporate visual action vertex into constructed graphs, capturing the relationship between objects and effectors. Inspired by the encouraging properties of graph representation, we naturally ask the question, can we formulate video pre-training as graph-to-graph generative modeling, enabling policy learning on limited action-labeled data? However, 7 challenges must be overcome. First, the source video and target scene often exhibit substantial embodiment discrepancy, hindering the transfer of the learned action knowledge. To address this issue, we propose the action-informed transferable graph representation, which extracts visual action vertex by abstracting key interaction points of the embodiment. Furthermore, the representation incorporates vertex on relevant objects, independent of specific embodiments. Second, the properties of distinct objects exhibit significant variability, such as stiffness, inhibiting the graph modeling network from capturing diverse object behaviors. To address this challenge, we propose to infer properties from historical observations and integrate them into graphs, facilitating predictions for objects with distinct properties. Third, modeling long-range dependency is crucial for capturing spatial relations, but directly expanding edge construction range potentially overwhelm important internal structures. To optimize this trade-off, we present a hierarchical architecture, integrating global vertex for long-range information. Based on the above analysis, we present GraphMimic, a novel approach that formulates video pre-training as graph-to-graph generative modeling. Our extensive experience exhibits that our GraphMimic achieves superior performance with only 20% of the data required by baselines, and significantly outperform them with identical data volume. GraphMimic first constructs graphs within video frame. Then, the generative modeling network is pre-trained to generate future graphs conditioned on the constructed graphs. It predicts object properties and establishes the hierarchical structure to capture important local structures and spatial relationships. Aiming to generate future graphs, the policy network predicts robot action conditioned on these generated future graphs through future learning from action-labeled demonstrations. We first construct action-informed graph representation based on the task description and an image observation. The object graph dynamics describe the change in object states irrelevant to the agent embodiment, enhancing the cross-embodiment learning ability. Furthermore, the incorporation of visual action vertex enables our approach to capture object embodiment interactions. Constructed graphs. The objective is to pre-train a model on videos for predicting future graph sequences. To facilitate the prediction of future graphs across different objects, we model object properties. Specifically, we retrieve object-centric graphs and track vertex sets across the historical observations. This historical information is encoded into object properties, which is incorporated into the constructed graphs. Then, to establish the long-range temporal dependencies, vertices are clustered with the root global vertex added to each cluster. Edges are then constructed to connect the hierarchical structure. Our graph condition policy takes the generated graphs, the current observation, and the robot proprioception as input, predicting a sequence of actions. We first investigate the ability of GraphMimic to provide accurate and expressive state representations. Our method, trained with only 2 action-label trajectories for each task, outperforms the latest method ATM and UniPy, which employ 5 times as many action-label trajectories. When trained with 10 action-label trajectories for each task, our method surpasses all baselines, achieving an improvement of over 70%. Real-world experience demonstrates that our GraphMimic maintains superior performance even when utilizing merely 20% of action-label data required by the baseline. We then investigate the ability of GraphMimic to provide easily transferable manipulation knowledge, facilitating learning from cross-embodiment video data. Our approach demonstrates superior performance when trained on merely 2 action-label trajectories per task, and achieves an outstanding 70% success rate with 10 trajectories. We use human videos to train the graph modeling network and use action-label demonstration trajectories to train the graph-guided policy. Experimental results demonstrate that our GraphMimic effectively facilitates the transfer of manipulation knowledge from human videos to robotic systems, providing expressive guidance for control policy learning. Comprehensive ablation studies are conducted to investigate the fundamental designs of our GraphMimic approach. The effects of this design are assessed by measuring the success rate in robot-to-robot transfer experiments. That's all. Thanks for your attention.